Now, the absolute maximum shear stress theory and the maximum distortion energy theory can both be used to predict failure in ductile metals. But they're a little bit different. The absolute maximum shear stress theory is great because it is so simple and easy to apply. Mathematically convenient, suitable for sort of back of the envelope calculations, and it's pretty good. When you take the results and compare that to an actual test, where you predict when failure will occur and then test when failure does occur, it lines up pretty well, but not perfectly. If you have situations where a point in an element experiences both normal stress and shear stress, then the maximum or the absolute maximum shear stress theory will predict failure to occur at slightly lower stresses than failure actually does occur at. So it's a little bit conservative. If you use the absolute maximum shear stress theory to design in those situations, you end up over-designing objects or components or materials by a small margin, and that's not a problem in most cases, but in some cases where, let's say, a weight of whatever is being designed is a huge concern, then you really don't want any over design to occur. You want the system that you're designing to have a safety factor that is exactly your target safety factor. You don't want it to be over-designed from there. Or if, for example, adding extra material to a design is going to reduce, or if adding extra material to a design is going to result in significantly increased costs, then you would want to reduce that. So let's just make a note of that. So when point experiences both normal and shear stress, then there are absolute maximum shear stress theory underestimates strength of the material slightly. Okay. And if this is a concern, so when this is a concern, then we turn to the maximum distortion energy theory. Maximum distortion energy theory. This theory is also known as the Vaughn misses failure criterion. You might have played around with finite element mapping of stresses in SolidWorks, for example, finite element analysis of stresses, and produced what are called the Vaughn misses stresses. So those are given by the maximum distortion energy theory, and we'll see the equation that's used to calculate those as we look at this theory. So the results of this maximum distortion energy theory, it predicts failure almost perfectly. When the maximum distortion energy theory says a material is going to fail, that matches up very, very, very closely with experimental reality. So what I'm going to do is I'm going to take you through the theoretical background of this theory, and then we'll build up the equation that the theory's based on. It's it doesn't take very long, and it's interesting to see where the concept comes out of. Okay. So let's go ahead and do that. So we know that for any element in a material, we can or any point in a material, we can represent the stresses at that point using an in-plane element. Let's say that let's just say for argument that we've got an in-plane element that looks like this, where we've got some stress in the y direction here, and we've got some shear stress too. And maybe this is the xy plane, so this is going to be tau xy. Right? We know that for any element like that, we can rotate the element to some angle and find an orientation where we only have normal stresses acting on the element. So those would be the principal stresses. So we've got a stress like this, which is going to be sigma y prime, and a stress like this, which is going to be sigma x prime, let's say. What the maximum distortion energy theory says, or the way it starts, is by saying we can take an element like this that is under a state of principal stress, and we know we can always get to a state of principal stresses by rotating the element in the proper orientation or doing our analysis in the proper orientation. We can take an element like this and we can represent this stress state as the summation of two different stress states. Okay, so we can say that that single stress state is the summation of two stress states acting on the same material. Just move that over marginally. There we go. So everything's nice and symmetric. So we can say that that stress state is the summation of what's called the average stress. So if we calculated the average stress between sigma y prime and sigma x prime, so here we've got sigma average. If we look, sigma y prime is a tensile stress and sigma x prime is a smaller compressive stress. That's just what I've drawn. So the average normal stress, if average normal stress is calculated the way we normally do here by 1/2 sigma y prime in this case plus sigma x prime, then it's going to be a small tensile stress, smaller than sigma y prime. And that acts on here all sides. So this is the average normal stress in both directions. Now, if that's one component of the stress, and this is called the hydrostatic component of stress. Why is it called the hydrostatic component of stress? Well, of course, because the stress is the same in both directions, right? Just like hydrostatic pressure being the same in all directions. Hydrostatic stress the same in all the directions. So if that's the average stress and we want to add another stress state onto that to get back to the stress state that we started with above here, then the stress here in the y direction needs to be whatever sigma y prime was minus our average stress. Okay, and it's worth noting here above, I should have put this down, that sigma y prime, this is our first principal stress here, and this is our second principal stress there. So let's just do a replacement here and put that like that. And then if we're going to be adding or taking the difference between our average stress and sigma x prime, which was a compressive stress, then to get that sigma x prime back, we need a larger stress here. So this is sigma 2 minus sigma average there. Right, so that's what the other component of the stress that we need to add on to the hydrostatic component looks like. So this component of the stress is called the distortional component of stress. Okay, so unlike the hydrostatic stress, which is uniformly trying to cause the material, uniformly acting on the material to expand or contract it, the distortional stress is the component of stress that's trying to change the shape of the material. So in the example that I've drawn here, that distortional stress is the component of stress that's acting to make the piece of material elongate and thin. Okay, just get rid of that. There we go. All right, so what the maximum distortion energy theory says is that the hydrostatic component of stress does not lead to failure of a ductile metal. Right? You can apply as much hydrostatic stress as you want, as long as the stress is the same in all directions, then your material will not undergo failure. And it's only the distortional component of stress that is responsible for failure. And more specifically, it's not just the distortional stress, but it is the energy associated with the distortional stress that causes failure. Okay, so putting that into words, the theory says failure in a material will occur when the energy associated with the distortional component of stress reaches the distortional energy that was present when the material yielded in a uniaxial tensile test. Okay, so failure in a material will occur when the energy associated with the distortional component of stress reaches the distortional energy that was present when the material yielded in a uniaxial tensile test. That is the maximum distortion energy theory in words, or the concept behind it. Okay, so let's go through the, this is not going to take long, but the short mathematical process of building up the equation or deriving the equation for the maximum distortion energy theory. So what we need to do is, this needs to be done in 3 dimensions when we build this equation up. So we need to start with a volumetric element here. Okay, so this is our volumetric element, and we're going to say we've rotated this volumetric element so it's under a state of principal stress, so there's no shear stress. So we'll call this the first principal stress there, and this the second principal stress there, and this the third principal stress there. Okay, we don't need that last one. There we go. Okay, so what we need to do is write an equation that describes the energy that's associated with the distortional component of the stress that this element is experiencing. Okay, so what's the relationship between energy and stress and strain? Well, the relationship's really straightforward here. So if we look at just a stress-strain diagram, normal stress, normal strain, we know what the stress-strain diagram for ductile material looks like, something like that. If you take the area under the stress-strain diagram up to any point, let's just say it's that point there, then you're taking the integral of stress with respect to strain. Now let's look at the units of that. You've got stress in newtons per meter squared if we're dealing with SI, strain in units of meters per meter. What's that? Newton meter, that's work, that's a joule, and on the bottom you have meters cubed. So the area within a stress, or the area under a stress-strain curve, gives you energy per meter cubed of material. That's called strain energy. It's the energy that you need to put in per cubic meter of material to extend it by whatever strain amount you're integrating the curve up to. Now, if strain energy we represent by giving this the symbol U. Now, if you're below the yield stress, so if our stress is below the yield stress, then we know we're in the linear region of the curve, and that area is simply the area of a triangle, right? 1/2 sigma multiplied by epsilon. So, right, for this element that we have above, the total strain energy that's associated with the stresses that that element is experiencing is given by the following. U is 1/2 of our first principal stress multiplied by the corresponding strain, and then we add on the energy from the other components of stress. So similarly, 1/2 sigma 2 epsilon 2 plus 1/2 sigma 3 epsilon 3. Okay. Now, what I want to do now is eliminate all the values of strain and write those in terms of stresses so that we've got U as only a function of stress. So we want U as a function of stress is only, so that we can substitute in for the distortional component of stress. We can sub sigmas for their distortional components. Okay. So we know that writing strain in terms of stress isn't too complicated, right? If we've got just a piece of material here, and it's under just one stress, let's say sigma 1 here, then we know that the material is going to elongate like this. And we know that stress is related to strain by that relationship. So sigma 1 equals modulus of elasticity multiplied by strain. So our strain is sigma 1 divided by modulus of elasticity. Okay, and the relationship between strain in that direction and strain in the other direction is through Poissons ratio, right? We had Poissons ratio, nu equals the lateral strain, which would be the strain in the second direction. So we've got epsilon 2 divided by epsilon 1 with a negative sign in there to indicate that those strains are opposite. One's a elongation, whereas the other one's a contraction. So if we flip that around, we can say that epsilon 2 is minus epsilon 1 multiplied by Poissons ratio, or in other words, it's the stress divided by, that should be an E there, not an eta, multiplied by our Poissons ratio there. Okay, so keep that in mind. You know all that, of course, but things are a little bit more complicated than just writing that relationship there when we have stress in multiple directions. So now imagine that we have a piece of material that's under stress in this direction, sigma 1, and also under stress in the horizontal direction. Let's say that's sigma 2. So if we think about the stress in the strain, in the direction of sigma 1, so the strain in the vertical direction, epsilon 1, what do we have? Well, we've got the elongation that's being produced by sigma 1, right? So that's going to be given by sigma 1 divided by the modulus of elasticity. But because of the presence of sigma 2, the stress in the horizontal direction, the result of the stress in the horizontal direction is going to be a contraction of the material in the vertical direction. So we're going to have a negative contribution from sigma 2, right? So that is going to be given by the Poissons ratio multiplied by sigma 2 over the modulus of elasticity, just like we had above. Okay, and then if we had a stress in the third direction, we'd get the same thing. So we'd also have Poissons ratio, stress in the third direction, divided by modulus of elasticity. So this gives us an equation then that relates strain to the stresses in all three directions. So we've got 1 over modulus of elasticity, and then sigma 1 minus Poissons ratio, sigma 2 plus sigma 3. Okay, and you can write similar equations for the strains in the other directions. So the strain in the horizontal direction, or the direction of sigma 2, is 1 over the modulus of elasticity, and then sigma 2 minus Poissons ratio, sigma 1 plus sigma 3. And strain in our third direction, which would be here into the plane of the screen. If I was drawing this as an actual volumetric element instead of an in-plane element, would be given by 1 over modulus of elasticity, stress in the third direction, or the third principal stress, and then the summation of sigma 1 plus sigma 2. Now, these equations that I've written here are what is referred to as material property relationships. These are called material property relationships. Okay, so what we can do is we can take those material property relationships and use the equation for eta 1, for example, to substitute. We can use that to substitute in for the equation for epsilon 1, sorry. Substitute that in for epsilon 1 in this equation here. So let's do that. So we want to take this equation here. Okay, and we're taking our material property relationships right here. Okay, and we're just going to take the equation for epsilon 1 and pop it right down in here, and then do the same thing for epsilon 2 and the same thing for epsilon 3. So we have an equation for our strain energy density U only in terms of stresses. So for the first term, for example, we'd have 1/2 sigma 1 multiplied by 1 over E, sigma 1 minus eta, sigma 2 plus sigma 3, right? And then plus, and so on and so forth. Okay. Now we've got an equation that's only in terms of stress. So now we can sub in for the distortional stress. Okay, so to do this, we're taking our equation for total strain energy and we're converting that into an equation that gives us just the strain energy associated with the distortional stress. So to do that, we need to take sigma 1 and substitute in our distortional component of stress, which was sigma 1 minus sigma average, okay, the average stress. In this case, right, where sigma average now, because we're dealing with a triaxial state of stress, is 1/3 of sigma 1 plus sigma 2 plus sigma 3 here, okay? So if we do that, and we do the same thing for sigma 2 and sigma 3, sigma 2 would become sigma 2 minus sigma average, etc. So if we do that, then we get an equation that looks like this. UD is 1 plus Poissons ratio over 6 times the modulus of elasticity multiplied by the differences between all the different stress pairs squared. So we've got sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared. Okay. Now this this here gives us the distortional component of stress. And now what we want to do is we want to equate that now to what the distortional component of stress was at the point of yielding in a uniaxial tensile test. So now we equate UD to UD at yield during a tensile test. Okay, so that's easy. If we're doing a tensile test, a uniaxial tensile test, so that's applying tension in one direction, that's exactly what the what we've done in our labs, right? So the loading situation is just like this, and you know, for any point in the material here, we can draw the element and it's under a state of principal stress, just has sigma 1 like that, and sigma 2 equals sigma 3. The stresses in the other directions are both 0. So if we take this situation and apply it when sigma 1 gets to the yield stress, okay, I'll write out sigma yield instead of sigma y to avoid any confusion. If we apply this when sigma 1 reaches sigma yield, we can use the expression that we developed above here for strain energy density, or the distortional component of it, to figure out what the distortional strain energy in this material was that we're doing the uniaxial tension on at the point when stress reached the yield stress. Okay, so we can say that let's get some black there. UD at yield equals, okay, 1 plus Poissons ratio over 6E. Here we go. We've got sigma 1 becomes sigma yield. Sigma 2 is 0, right? Plus 0 squared. Sigma 2 and sigma 3 are both 0 above, so we've got 0 plus 0 squared, and then plus sigma 3 is 0, plus sigma 1 is sigma yield, okay, squared. Now it's just getting pretty cramped up here, so let's just move that over and allow this to breathe a little bit. There we go. Let's just fix this up because it got pretty ugly at the end there. Okay, yield squared, and close our bracket. Okay, so if we do some work on that equation, 1 plus Poissons ratio over 6E, what? We just have 2 sigma yield squared. Okay, so now what we do is we just equate UD at yield with our expression for UD. So now we let UD at yield equal UD, which gives us 2 times our yield strength squared equals those differences. Sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared. Okay, and that is, see, I told you it wouldn't take that long. That is the maximum distortion energy theory. Okay, now the relationship to Vaughn-Mises stresses, right? If you have a plot of Vaughn-Mises stresses, what that is plotting is just the right-hand side of that equation divided by 2, square rooted. So if we look at the Vaughn-Mises, there's only one S in that, Vaughn-Mises stresses, then what that is plotting is sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared, all divided by 2 to the 1/2 here. Okay, so now you know when you run finite element analyses and you get Vaughn-Mises stresses out, what that is actually plotting. Okay, and that's why you can compare whatever the Vaughn-Mises stress is to the yield stress, because that's, that's where that equation comes from. Now, as it turns out, so going back to our equation here for maximum distortion energy theory, in most cases, the stress in that third principal direction, so our sigma 3s in here, are actually 0. So in many or most cases, sigma 3 equals 0. right? So the equation reduces to, and if you look at all of the problems that we've done in this course, and there are a lot of very realistic problems that we've done, you know. Most of them are based on, or many of them are based on real situations. If you look at all of those problems, in every single problem, the stress in that third direction has been 0. So you don't often encounter situations, or you encounter situations less frequently when you've got stress in all 3 directions, and that's just the nature of the world we live in, and how we move through it and use it. So this equation reduces when the stress in the third principal direction is 0 to the following. The yield stress squared equals the first principal stress squared minus 2 times the difference of the remaining principal stresses plus the second principal stress squared. And the more useful form of this is to include a safety factor. So that's the form that I'd say that you should use. So if you're doing that, the safety factor has to, or should go underneath the yield stress there, and needs to be squared as well. So we've got sigma yield, sigma y, divided by the safety factor. That's all squared equals sigma 1 squared minus sigma 1, sigma 2, the product of those, plus sigma 2 squared. Okay. And just so you remember what sigma 1 and sigma 2 are, right? Don't forget that sigma 1 here and sigma 2 are the principal stresses from Moore's circle. Principal stresses from Moore's circle. Okay. So the application of the maximum distortion energy theory follows everything that we were doing for the absolute maximum shear stress theory, right? You figure out where your point of interest is, define the stress state of a volumetric element at that point of interest, draw the in-plane representation of that element, plot Moore's circle, and then to apply this theory, what you need to do is calculate the principal stresses and then apply the theory. In the previous theory, the absolute maximum shear stress theory, we needed to know the signs of the principal stresses, but we weren't as concerned with their value. Once we knew the signs, then we just found out what the radius of the circle was. So we'll just make a note of that. So to apply theory, right, what do? We define point of interest. Let's try that again. Interest in object. And then we define the stress state of our point. And then we draw our in-plane element, and then we plot Moore's, let's put the H before the R, Moore's circle, and out of that we get our principal stresses. And then we can apply the theory. Right? So easy. Easy. Okay, so let's do an example here. Okay, so we'll say that we're drilling maybe a well, maybe it's for water, right? So we've got some sort of motor, right? And it's attached to a pipe here, which has some sort of cutting bit on the end of it. Okay, and we're rotating the end of that pipe with the cutting bit around to bore a hole in the ground. So let's draw our ground here. There we go. So we're cutting out a hole in the ground, something like that. Okay, and let's say that this pipe, let's call this the drill pipe, has a cross section that is looking like this. So it's got a 3-inch outer diameter, and it has a, what do we have here? A 2-inch inner diameter. Okay. Let's get a problem statement here. So the motor applies 3,000 foot-pounds of torque to drill pipe, which is pressed into the earth with a vertical force of 12,000 pounds. Okay. And we'll say what we want to do is we want to choose a suitable material for that drill pipe for a safety factor of 2. Choose suitable material for pipe using safety factor equal to 2. Okay, so we've got our torque shown there. So here's the 12,000 pounds, and here's the 3,000 pound feet. So let's just turn this terrible drawing that I've made there into an actual free body diagram. Okay, so here we go. So here's our pipe like this. So we've got the motor that's applying some torque to the top. That's 3,000 pound-feet. So this is torque from the motor. The bit at the bottom, if this thing's rotating at a constant rate, is taking out the equal amount of torque, or is it applying an opposite amount of torque? So this is TB for the bit equals TM from the motor. And then we've got what? A compressive load of F equals 12,000 pounds, which has to be balanced out by the rock or earth that it's cutting through. So here we go. Our force at the bottom is equal to the applied force F. Right, so there's our free body diagram. So what we want to do here is the typical thing of trying to pick the location that's going to experience just maximum stress as a starting point. And then that will be the location that we draw the volumetric element for and plot Moore's circle for and apply the theory to. So this is much the same loading situation as we've seen before, one axial load and a torque. So from the axial load F, that's going to create a normal force within the pipe, and the normal stress due to that normal force is going to be the same at all points of the cross section, so it doesn't matter what point we choose there. The torque, however, is going to create shear stress, and that shear stress is going to be maximum around the circumference. So for our point of interest, we can pick any point on the circumference. So for our point of interest, we can choose any point on circumference, because all these experience maximum stress. Okay, so let's just take our point A right there. Actually, let's move it off here a bit so our drawing looks a little better in terms of perspectives here. So we could draw a cross section where point A is sort of dashed out like this, and then the center of that section's there. So we've got our axes going something like that, maybe. So X, Y, Z. There we go. So our volumetric element at the location of A is going to be, actually, let's move to another page, and we'll actually take our section cut, and actually, let's just take the shortcut and just erase that down there, and then that becomes our free body diagram after we've taken the section cut, and these down here become our internal forces. Right, this was a little short anyway, that was bugging me. So there we go. Now it's just ugly. Okay, there we go. All right, so now let's draw the volumetric element that's located at point A. It's nice to do this all on the same page, so you've got everything to look at and refer to here, at least while you get on the directions of the stresses. Right, so this is my element at point A, and let's mark out the bottom plane. Okay, so that is the bottom face of that element is the face that's in the section plane of our object. And from the internal force now, changing this to an internal force, this is now labeled N, and we'll just change this torque here to be labeled as we normally would the torque about the z-axis. So from our normal force N, that's going to create a normal stress. There we go. Okay, that's sigma subscript N. And then our torque is going to create a shear stress on that bottom face in the direction of the torque, like that. Okay, there we go. So that is tau Tz. Okay. So let's grab this drawing here, and we'll just copy it and take it to the next page with us. Okay, so let's get values for those two stress quantities. So we've got sigma N is N divided by A is 12,000 pounds. Pi over 4 outer diameter squared minus inner diameter squared. Okay, 3 and 2. So that gives us a value of, drum roll, 3.1 KSI. Now for our shear stress, tau Tz, T rho over J. Our torque was 3,000, but that's pound-feet, remember, so we have to change it to pound-inches. rho, the distance, our point of interest, is away from the center of the pipe, so that's half of the outer diameter. So we've got 1.5 inches, 3 divided by 2 there. J pi over 2 radius to, that's a 3, radius to the 4th power, and inner radius to the 4th power. Okay, there we go. So that's giving us 8.5 KSI. Brilliant. Okay, now we can go ahead and draw the in-plane representation of that volumetric element. So we had X, Y, Z there. So we want to draw this element in the ZY plane, Y, Z, and our in-plane element looks like exactly as you'd expect. It's just the front view of that, where that shear stress is down, that's up, that's this way, that's that way. Okay, and then this, we'll call this, relabel it sigma z because it's the stress in the z direction. And this is going to be tau zy because it's the shear stress in the zy plane. All right, and now we've got values for those. So now we can go ahead and do the calculations that we need to do to plot more circles. So we can figure out what the average stress is, which is going to give us the location of the circle's center. So that's the average between sigma z and sigma y there, right? Which is just 1/2 of sigma z, and remembering that that's a compressive stress, so it needs to go in as a negative value. Let's just specify that this is, actually that was 0 in the other direction, so we'll just leave that out. Okay, so we've got about 1.5 there when we do some rounding, KSI for our average, and then point A, stress state on the element's right-hand side, right? So we've got sigma comma tau for the right-hand side equals what? 0 comma 8.5, and that's negative 8.5 because that shear stress is pointing downwards. Okay, let's go ahead and plot more circle now. Okay, there we go. So we're going to label positive shear stress down that way, positive normal stress down that way. Our center of our circle was located at minus 1.5. So this is C, and we're doing this in KSI. Okay, and then this reference point, point A, was at what? 0 minus 8.5. So here we go. That's minus 8.5. Obviously not completely to scale, but that's okay. That's point A. And the radius of our circle goes from C to A, radius R there. Then let's draw the circle. Perfect. A little bit off-centered there, but that's okay. So we've got our first principal stress out here because it's the larger absolute value, and our second principal stress there. So easy to calculate what the values of sigma 1 and sigma 2 are. Once we've done that, then we just need to apply the failure theory and the problem's done. So easy. So in order to calculate sigma 1 and sigma 2, what we need to do is just figure out what the radius is first. That would be helpful. So we've got R is the square root of what? 1.5 squared plus 8.5 squared gives us 8.6 KSI. Okay, so for sigma 1, we calculate that by taking the value of C and subtracting R from it in this case. So we've got minus 1.5 minus 8.6 equals minus 10.1 KSI. And then for sigma 2, we take C and we add on our value of R. So minus 1.5 plus 8.6 gives us 7.1 KSI. So now we're in a position where we can apply our maximum distortion energy theory. So that is sigma y divided by our safety factor squared is sigma 1 squared minus the product of the principal stresses plus our second principal stress squared. And what we're looking for here is the yield strength, sigma y. So we've got sigma y divided by our safety factor, which we said was 2 squared. Now remember to put in the signs when you're doing this, not so much a concern for the ones that are squared, obviously, but I'll still put them in just to demonstrate that we are worried about signs. So we've got squared minus 10.1 multiplied by 7.1 there plus 7.1 squared. Right, so out of this you get the required yield strength for the material, which comes out to be 29.9 KSI. So if you were to look in our material properties table and choose a material that had a yield strength of around 30 KSI, what would we have? Yield strength around 30 KSI. Get an eraser there. Right, so what are the candidates? So we've got 37 there, 30, 36. Right, so the closest one is 36, so A36 steel. Or what was the other 31? 304 stainless steel if we want to go stainless. Actually, I forgot that we were just marginally below. So therefore, 304 stainless or, right, A36 are fine choices. Okay, so that's all there is to the maximum distortion energy theory, aka the Vaughn misses failure criteria. So now you're well equipped to predict the failure of ductile materials. Okay, I will see you next time for the last lecture in the book, lecture 18, all about how do we actually measure the stress that something's under. Okay, I'll see you then for that.